Hello everyone and welcome. This video is going to be a bit like my older videos where this is a PowerPoint presentation with pictures and graphs and slides and so on, and I will try to explain to you what you actually see. So the title of this video is 1.75mm PLA under pressure. What does that mean? I try to investigate how much pressure the OmniaDrop extruder can exert onto the nozzle. So the OmniaDrop extruder is an extruder hot end combination that has a dual drive gear system. This dual drive gears drives a filament down this filament path, then into the heat break, and then into the nozzle, where the filament is then being extruded through the nozzle orifice. The OmniaDrop has this so-called idler. This idler can pivot around this axle, and this spring right here puts a force onto this idler, which is then converted or exerted or transferred, that's the right word I'm looking for, transferred onto the hop gear and then onto the filament where it's pushing on. The experimental setup is actually quite straightforward. We want to measure a weight or a force, and from your household appliances, you know a certain household appliance that can do that. That's your scale, and that's what we're going to use here as well. A scale just has as well a load cell in it, and this load cell is then attached to this experimental setup, which tries to remodel the distance between these hop gears and this nozzle tip. So the distance between these hop gears and this load cell is exactly the same distance as you would have between the hop gears and the nozzle of an OmniaDrop extruder. So this load scale then sends an analog signal to this HX711 load cell amplifier, which then converts this analog signal into a digital signal, which is then sent to an Arduino, and with some code it will send that, the Arduino then will send then the results back to my computer. The load cell itself has a weight limit of 20 kilograms, and it's just a metal bar. And if you wanted to know further how a load cell works, it basically just measures a minute deflection which it experiences and converts that to an analog signal. During the experiment, there's one parameter that was changed physically and not just in the firmware, and that was the so-called spring tension. The spring tension I measured in millimeters, so 1, 2, 3, 4, 5. And if you see that, that means basically the distance between the extruder main body and this null nut right here. So the greater the number is, the more the spring was tensioned and the more force was transferred onto the hop gears, which then transfers that pushing force onto the filament. So the methodology is quite straightforward. We have two parameters that we're investigating. One was the spring tension, as I mentioned before, and the other is the stepper motor current. Stepper motors have usually a data sheet, and in this data sheet it mentions a so-called rated current. And this rated current is the, in air quotes, maximum allowed current you can supply to that motor. You can supply more, but that will damage the motor over time. And one of the issues of this rated current is that if you actually set that rated current, the stepper motor gets quite hot, like 70, 75 degrees until up to, apparently 80 degrees, I was told. So for 3D printing purposes, we usually use 60 to 70% of that rated current, and just to make sure that the stepper motor doesn't get too hot. So the procedure of the experiment is quite straightforward. I loaded the filament until it reached the scale, and then I ran this G-code right here. The first line of this G-code allows for so-called cold extrusion. Your printer has set in their firmware a minimum extrusion temperature, and that is usually set at around 170 degrees Celsius. So any code that involves the extruder and the hot end hasn't reached 170 degrees Celsius will be ignored. So to overcome this or disable that function, you have to use that line of code, M302P1. Then the extruder position is set to 0, and then we're going to start extruding 2 millimeters of filament at 30 millimeters per minute. For reference, it is actually a quite slow extrusion because I use this lower extrusion number to have a higher resolution on the scale. So because if you go too fast, the scale doesn't only send signals in incremental time limits or time intervals, so you might miss, in air quotes, a maximum reading, for instance. So if you go a bit slower, you will get a more accurate reading. I noticed that if you go too slow, the stepper motor is turning too slowly and you actually lose torque. So, but 30 millimeters per minute was a kind of sweet spot. The last code is just disables the stepper motor so you can turn it. The code on the Arduino took the 20 highest numbers during one run and took an average and then sent that to my computer. Why to 20 highest numbers? That has to do with a lot of factors, which I'm going to explain later on. To have I will show you a graph and to explain to you why I chose this exact approach. I think this depicts the potential of an extruder, or the actual the pressure, what happens inside a nozzle, more accurately than it would a different methodology, like for instance running averages or absolute peak maximum. So later on I'm going to explain why I did that. For each data point, I let this G code run basically 5 times, each time obviously cutting that piece of filament that was used away and then reloaded it and then run it again. So that's 5 times, and then took an average again to get more accurate picture of everything. So let's go to the results. So in this column right here, we have the current in milliampere. The pancake stepper motor has a rated current of 1 ampere, so 1000 milliampere, and then I go down in 100 milliamperes increments down to 400. As a reference, I mentioned that we use around 60% of the rated current for day-to-day use on 3D printers. So the recommended current you should set for your pancake stepper motor on the OmniaDrop is 600. So that row is probably the most interesting one for you. Then the spring tension, as I mentioned before, is the distance between the extruder main body and that knob nut. The minimum should be, by the way, 2 millimeters. If you set it to 0, so basically the nut is touching the extruder body, then you get a very poor force buildup inside the nozzle. Because I did that run, but it's just not very exciting to see. It's just one column of 30 newtons, 30 newtons, around 30 newtons, 30 newtons, and so on and so forth. So it basically doesn't exert a lot of force onto the nozzle. So never set it to 0. Your minimum should always be 2 millimeters. And up to a maximum of 5 millimeters. After that, the spring reaches its limit. So 5 millimeters is basically the limit of that spring. You shouldn't go beyond that, because after that, the spring will start deforming and over time will exert less force onto the idler. So 5 millimeters will always be your maximum. So let's go row by row. So 400 milliamperes, we start off with 35 newtons, then go on to 33, 32, and 31. And you should hopefully now be just as confused as I was when I first started noticing this trend. Why do the numbers go down and not up? You exert more force onto the filament, it should grip better, it should exert more force, but no, it just goes down. And I thought about that problem, and soon it dawned on me that as you increase the spring tension, also the spur gears on the hop gears, or the dual drive gears, are meshed closer or are forced together stronger, and that creates more friction inside the gears, and that has to be overcome first of all. So you lose some torque to that friction, and that's why these numbers actually go down. That is the most likely explanation I could find to that phenomenon. Same goes for the 500. We start off high, start lowering, going down, and then the same for the 600. We start higher and go down, and then at 700 we actually see higher numbers going with spring tension. And the most interesting part about the 2 millimeter is we hit kind of a peak. So around 62, 63, apparently 65 as well, newtons on force is the maximum for the 2 millimeter spring tension. After that, it just cannot exert more force. We have a bit of an outlier with the 1000. I'm going to explain later on why these outliers happen. Same goes for the 3 millimeter. We kind of hit this peak at 72, 73 newtons. Again, 10 newtons more as the 2 millimeter spring tension. And you can see again a bit of an outlier, 1000 milliamperes. At 3 millimeter has a bit more. With 4 millimeters, we kind of reach a maximum already. But as you can see towards the 5, that at 900 milliamperes we can still go a bit above, and we get a bit better results at the 900 milliamperes. And you're going to see later on why the 5 millimeter is the absolute maximum, and also it can exert the most force. So I thought that is quite interesting. So we have this nice color gradient going from darker red here to up to a very dark green. And as apparently the maximum force you can exert with the small stepper motor using the absolute rated current is apparently about 10 kilograms, let's say that like that. So this is table, I call it the strip or grip table. It is actually quite straightforward. I just did the experiments, and while I did these experiments, I looked at the filament that was used, either it was stripped or not. And you can actually, sometimes the extruder started skipping steps, and sometimes it started stripping the filament. And if it says no here, that basically means that the extruder rather skipped a step than started grinding the filament. That means the torque of the stepper motor was lower than the grip of the dual drive gears onto the filament, if that makes sense to you. And if it's the other way around, so if the torque was higher than the grip on the filament, then the dual drive gears started stripping them. And this yaw factor was, the yaw section was, it sometimes skipped steps, sometimes stripped it. Probably over time, it would have stripped it anyways. So the yaw would probably turn into a yes if that goes on too long. The whole extrusion process, let's call it that. And what is interesting to note is if you go back to this table before, is that you can see that we hit this kind of maximum here, like 60 newtons, and then it just starts, and then it starts stripping the filament. As you can see, 700, we reach our maximum, and it just starts stripping the filament. That means, again, the force of the spring was lower than actually could have been converted. And the same goes for the 3 millimeter. You can see the 70, 83, and it starts stripping it. And on the 4 millimeter, yeah, we already are pretty close to the absolute maximum we can transfer, but probably with the 5 millimeters, we're on the safer side. Let's put it that way. But 4 millimeters is already pretty good. So 4 millimeters, you probably already have very nice behavior. Now to explain why I chose the 20 highest numbers and how a run would actually look like if you would have logged it in a table, in a graph. So we have here the 5 millimeter spring tension at 1000 milliamperes, and you can see that the grip is nice and strong, and it keeps on exerting more and more force and compressing the filament ever more until it reaches the torque limit of the extruder motor, and it skips a step, drops down, and restarts the whole process of building up the pressure and then skipping a step again. And that would have gone on for quite a while. We can clearly see that better at the 3 millimeter spring tension at 600 milliamperes. You can see the build-up in pressure, and you see the gradients are actually exactly the same. So they build up the pressure always the same way, and then it reaches the torque limit, skips a step, and restarts again, and skips a step, and restarts again, and skips a step. There we have a bit of an outlier. It didn't quite reach the maximum, maybe didn't get that good a grip this time, or so on, I don't know. But now to the next part, which is, I think, the interesting part, is what happens if you actually have a stripping effect. So 3 millimeter spring tension, 1000 milliamperes. If you remember that 3 millimeter, it strips definitely the filament. So it starts building up this pressure, and as you can see, it could potentially reach the same number as the 5 millimeter spring tension at 1000 milliamperes. But since there is not enough grip, it starts stripping the filament, and you can see this decline, and it starts stripping it, and then you have the so-called regrip effect, which I called it. It starts then regripping the filament again, then losing again this grip, and stripping again, then regripping again, stripping again, regripping again, stripping again, until there's nothing left of the filament. And then probably if you would push that on, it would reach 0 basically, because it stripped away the filament. So, and why did I take now the 20 highest numbers? First, I just recorded the peaks, but that felt a bit like cheating. It felt like just take the highest number and just go excessive and say like, oh look how strong everything is and how well the torque is being transmitted from the stepper motor onto the filament and then onto the nozzle, it felt a bit like cheating. It really did, and I didn't feel good doing this. I don't think it would be a long-term measurement that you could use. So it's the absolute maximum, and then you start skipping a step. So you should probably go a bit below that, and probably be just a few newtons below that. It could keep up that pressure continuously without any issues. So as a next step, I just took a running average, but these running averages just didn't quite work out, especially for these stripped parts. It wouldn't also depict quite what kind of forces were happening inside the nozzle. So if I used a moving average, for instance, at the 3 millimeter, 600 milliamperes, you would get around 41, 42, I think, newtons it was. That is basically your running average. But that's not actually what kind of forces were actually possible inside the nozzle at that kind of setting. So that didn't feel like an accurate number either. And also an issue was with the running averages was that when the stripping occurred, that if you use a running average there, the strip and regrip effect wasn't always the same. So sometimes it regripped quite well and it could actually push again up until the same kind of forces it had, and it had a higher average then in the end. And then sometimes it completely failed to regrip and lost all kind of torque, and then you got these fluctuating numbers, and just didn't make any sense to use it that way. So what I did in the end is I tried to use the 20 highest numbers in the hopes that I would get like just a few newtons lower than the absolute maximum usually the run would peak at, if you know what I mean. I hope that makes sense, and if you would have done it differently, please leave that in the comments, because that would interest me to maybe use a more realistic approach if you think that is not realistic. So just leave a comment down there and tell me what I should do differently. So just as a quick out of interest, let's call it that, there is a possibility to also get a bigger stepper motor for the OmniaDrop, which has a body length of 33 millimeters. Or 30 millimeters, or 35, around that. I have to remeasure it. 33, I think it's 33 millimeters. And the small pancake stepper motor has 20 millimeters, so it has less torque than the bigger stepper motor. So I just switched them out just to see what happens. And since the bigger stepper motor has a rated current of 1.33 amperes, I decided instead of just using the current, I'm going to use the percentage of the rated current. So we have like maybe equivalent numbers. So at 100% of each one of the rated currents, we can compare them better. So that's why you can see here these percentages instead of a actual current of milliamperes or amperes. So the small stepper motor, like before, we have a spring tension of 5 millimeters, so the maximum absolute possible setting. And then we can see here that the bigger stepper motor actually always at the beginning starts performing very similarly, not that much better than the small stepper motor, but then it goes off and has already instantly at 50% of the rated current, nearly 50% more torque. That goes on again here, 20%, 20 newtons more. There we have 25 newtons, and it goes on 25 newtons, and the same here. And we kind of reach like a peak here. I don't have now a separate table where it says so, but this section right here, that's where it starts dripping. So even at 5 millimeter spring tension, we kind of reach a maximum again of the spring tension. A possible solution would be to use a stiffer spring that can exert more force, even more force onto the idler. That would be possible, and then probably we could get even a bigger torque out of the stepper motor. Transfer torque, let's call it that. The torque of the stepper motor was always there. It's always how well we can transfer that torque onto the filament. Just for someone who has a 3 millimeter OmniaDrop version, that doesn't mean these numbers are equivalent for your OmniaDrop 3 millimeter, because the OmniaDrop 3 millimeter has a different dual drive gear system, which has a smaller radii, which means probably we will get different results for that. I'm gonna do also experiments on the 3 millimeter version. So let's put this in a graph and let's see if we have any linear behaviors. And yes, we do. For the small stepper motor, for the pancake stepper motor, we have actually a quite nice linear behavior. And for the bigger stepper motor, we have kind of three linear behaviors. So at the beginning, we have like a nice also parallel move of to the small stepper motor. We have 3 points which could be linearly explained, and then it starts making like a skip at 50%. So suddenly turns up its performance, the big stepper motor, and has again a linear behavior up to this point of 80%. And then obviously due to the stripping effect of the filament, because the 5mm spring tension is not high enough to transfer more torque, we have this dipping behavior and again a bit of linear behavior, but so in theory you would need 3 linear functions to approximate these, 9 data points. However, for the small stepper motor, we can have a single linear function that it can approximate this function. And what is now interesting is that people are going to tell me now, well, what can we actually do with all these things? Like, that was a great presentation, Max, well done. It wasn't. But what can we do with these numbers? Why are they of interest to us? Personally, they're of interest because I always wanted to know what kind of pressures do we actually need to extrude PLA, for instance, at 60 millimeters per second for like 60 millimeters per second printing speed, 0.2 millimeter layer height, let's say, and 0.4 extrusion width. How much pressure do we need to actually extrude that filament? Because there are claims and stuff like how much pressure a extruder can, how much pressure it can build up. But do we actually need this kind of pressure? And where do we lose pressure? And what happens to, for instance, if you increase the pressure, and what happens then to the exudate swell? If you don't know what the exudate swell is, that's go back to the 1.75 versus 3 millimeter filament video, all the way back 2 years old from one of mine in my list. You can check it up. I explain there what exudate swell is, or what happens if you change the nozzle material. So if you use a nickel-plated copper nozzle or a stainless steel nozzle or the brass nozzle, do they behave differently, even though they're the same geometry on the inside and have the same nozzle size? But do these materials perform better or worse, or what happens there? Also, if you change the nozzle size, it also changes geometries. That's what E3D does. It's quite interesting to see. They have a nice technical drawings on their nozzle sizes, and you can see how they change a bit the geometries depending on the nozzle size, and that would be interesting to figure out if that helps or it doesn't help. So this could be it could be interesting to investigate. Also hot end sizes, so instance like a V6 style hot end and a volcano hot end. Do you need actually more pressure to extrude through a volcano? We can actually now measure that. We can see the performance of different hot ends. So how well do these hot ends transfer their heat onto the nozzle and then the nozzle onto the filament? So these combinations could be investigated. So there's quite a bit, and then you could go on to how well can we transfer torque with PTG, PC, ABS, nylon, and flexible. So do they all just perform the same like it did nice and linearly with like PLA did, or do they behave differently? So that could be investigated. So there's quite a bit what you can do, and what I think most personally, what is the most interesting part is you could now say, oh well, you could have just changed the current of the stepper motor and just said, okay, for this hot end I need a higher current for the stepper motor to extrude things, and the other one I need a lower current. But you never knew that there was a linear behavior. So now if you use an OmniaDrop and a pancake stepper motor, you can be assured that if you change the current to that stepper motor, you can actually change, you can know that it has a linear behavior, and you can actually say how much force was inside or could be exerted onto the nozzle. So, first of all, thank you for watching, and if you would like to see more videos like this, it would be great if you could comment which one you would like to see. So I have two things in mind as I could do for the next video is what pressures do we need to extrude PLA from a brass nozzle? So we would investigate an 0.25 millimeter nozzle, 0.4 millimeter, and 0.6 millimeter and see how they perform. Can we push maybe more filament out of one than the other, let's say? And the other one which I was thinking about is maybe do a 101 extruder video where I try to explain What's the difference between the extrusion multiplier and E-steps, which I sometimes see when people today even calibrate their E-steps, and I can explain you why that wouldn't be necessary anymore if a supplier of that extruder gives you already a E-step value. And sometimes you can see that in certain on Facebook and Reddit and so on, that people tell you, oh well, my extrusion multiplier was 410, oh no, mine was 398, and will try to explain why these numbers might be different, even though they shouldn't be. And as a next thing, oh no, an installed update. No, I don't want to install the update. How can we calculate, for instance, the torque that's being transferred from the stepper motor to the filament? So that's something we can also do in the 101. How does the tooth profile influence the grip on the filament? So probably you have noticed there are different tooth profiles on hop gears, and I maybe can explain you why these tooth profiles have been chosen, or why they could be advantageous or not. And then also I could do an investigation in do dual drive gear system actually transfer more torque to the filament than a single drive gear system. So in the earlier like for instance, the extruder on the Ender 3 has a single drive, so you have a ball bearing that pushes the filament onto a hop gear, basically, that pushes then the filament into the extruder, into the hot end. I'm sorry. So that's something I could do as well. So if you have any preferences in that regards, please leave that in the comments. If you don't want me to do any kind of these videos anymore, you can say that as well. I'm not going to take it personally. I'll still do my investigations. I will just then maybe not publish them anymore if nobody's really interested in them. I wouldn't mind. I would not take it personally. I still like doing them. For me, it's I'm a bit of extruder nerd, as you might have noticed. So for me, that's something I love to do. And if you like them as well, or don't, just comment on that. That would help a lot. So thank you for watching and staying that long and actually listening to me ramble a bit. And maybe I'll see you in the next video. Until then, bye.